Okay, I wanted to start us off with that simulation that I told you about the other day. So this is the second link in the notes from Monday. So the deal with molarity, again, is that it is defined as moles over liters. So if we're looking at this situation, I can't draw on this one, but if you look over at the left where it has the solute amount in moles and then the volume in liters, you just divide one by the other. So if you look in this case, there's a half a mole in a half a liter. So the the molarity shown on the right is 1 molar. We also could have 1 mole in 1 liter, and that would be 1 molar. If we had, let's try to get this one close, 0.3 in 0.3 liters. It's a little bit off, but it's about 1 molar, okay? And then as you add, so let's put this back to about a half a liter. As you add solute, or it gets more and more concentrated, we see the molarity go up, okay? If you were to add, let me bring this back down a bit. If you were to add water to this solution, so you're not changing the number of moles, you're just diluting it by adding water, your concentration goes down, okay? So that's the basics of molarity. So going back to the notes, I wanted to start us, we did some of these calculations. You need to feel comfortable using molarity as a conversion factor, either to get from volume to moles or to get from moles to liters. We did those dilution equations. We can use that either for diluting, adding water, and not changing the moles, or we can use it for evaporating. So the water gets smaller and the number of moles stays the same. But obviously, since molarity is moles per liter, the concentration, the molarity is going to change. Okay, so I did do this in maybe 2 of the classes, but I'm just going to go through this again. Now, since this is a video and you can easily pause it, I'm not going to sit here and wait for you to work a problem. So just go ahead and pause the video and work the problem and then check your answers. Watch me work through it if you need to. And I may talk kind of fast just because, I don't need to wait to have you catch up. You can always pause or rewind it a little bit, okay? All right, so we're starting with 175 mils of a 6 molar solution and excess aluminum, okay? So we want to ultimately go to mass of hydrogen. So we know that somewhere in the middle, we're going to do a moles of H2SO4 to moles of H2 conversion, okay? Just like the stoichiometry we did in the previous chapter. Now, in this instance, the way we get to moles of H2SO2 is not from grams like we did in chapter 4. It's from the volume, 175 mils. And we're first going to have to convert that into liters. That's a very common conversion you're going to have to do. And then we're going to go to moles. And the conversion factor here is the molarity. Okay. In previous stuff in the last chapter, we were starting with grams, so the conversion factor was the molar mass. And here it's the molarity. Okay. And then finally in this problem, we'll take moles to grams. So adding in this, actually working through the problem, molarity is moles per liter, and we can use it as that so the liters cancel out. And just since we're doing a balanced equation, we better be pretty specific about moles of what, okay? Now we do the mole to mole conversion factor. Sorry about that. And then finally, we're going to do the gram to mole conversion factor. Okay, so molarity is, we're told in the problem, it's 6 moles per 1 liter. That's what molarity means. 6 molar means 6 moles per liter. 3 H2 for every 3 H2SO4. And then finally, from the periodic table, H2 is 2.016. Okay, so 175 divided by 1,000 times 6 times 3 divided by 3 times 2.016 is 2.17 grams of H2 produced. So if we started with 175 mils of 6 molar H2SO4, it'll react with excess aluminum and give us 2.17 grams of hydrogen. Okay. Now for the next question, I'm going to change this slightly because I don't want us to do a limiting reactant problem. Okay. So let's just say it's excess copper. Okay, so similar problem. We're just going to kind of go through the same process. All right, so maybe the best thing to do here would be to stop the video, work it yourself since you've seen one example problem, and then you can check your answers. Not sure why we keep getting a mole-to-mole ratio that is always 2 to 2, 3 to 3, but we do. Okay, so this is 2.83 grams of silver produced. Okay, so make sure you can get that, you can reproduce that. All right, so our focus today, I'm just looking forward to make sure I know where we're headed. Our focus today is going to be on more of the conceptual stuff. So a little bit less problem solving, a little bit more just concepts. So if any of this feels confusing, you can always go read the textbook for kind of a different explanation of it. You can also watch the videos that are on Pearson, either the ones that are embedded in the textbook or the ones that are on like the general chemistry channel. And then lastly, you can always go to Khan Academy and look at their AP chemistry / general chemistry channel. Okay. All right. So we're going to talk just today. We're going to talk about things that are not just water solutions. Some of them will be water as the solvent. Some of them will be other solvents that are a little bit different. Okay. So you know from practical experience that not everything will dissolve into a liquid. So if you try to put sand in water, it is not going to dissolve, right? If you try to put oil in water, it is not going to dissolve. How do you know that? Because even if you shake it up, the second you kind of let it go and settle, it just separates and they're not mixed. It's not homogeneous. Okay. So what that really has to do with, the reason why that happens is because the interactions between the solute and the solvent must be stronger, more stable, lower in potential energy. So kind of just, all those mean the same thing. Stronger, more stable, lower potential energy. Okay, these are all, this must be true if the thing dissolves, right? So salt dissolving in water or sugar dissolving in water, the sugar-water interaction must be stronger than the sugar-sugar interaction and the water-water interaction. That's what makes it happen. That's why it's favorable, all right? The reason why this happens is it has to do with something called polarity. Now, we're not going to get into what polarity is in detail until the second semester. But it is, sorry, I had a school phone call. Take that one in a minute. It is important for understanding solutions, and so we have to just briefly talk about it. So you're not going to necessarily understand all of this and why this happens right now, but just understand the basics of what water looks like and why it's going to interact with certain things in certain ways. Okay, so the structure of water, this is our oxygen up here, and these are our hydrogens. The structure of water, the atoms involved cause oxygen to have a slightly better ability to attract the electrons in the bond that exists between oxygen and hydrogen. Okay, so what that does is it creates a slightly, this symbol means partial, a slightly negative charge on the oxygen atom. And as a result, it creates a slightly positive charge on the water molecule. So when we have those partial charges, we say that the water or that a molecule is polar, meaning that it has a difference in charge. So when we draw water molecules a lot of the time, we'll just kind of draw it as this is the negative side and this is the positive side, and show it like that. Okay. Now, when we dissolve an ionic compound like salt, sodium chloride, into water, those ions actually attract to the positive and negative sides of the water. So if you'll see, the chlorine is being attracted to the positive side of the water, and the sodium is being attracted to the negative side. And that interaction is really quite strong. This solute-solvent interaction is strong or stable, okay? Because again, like we've said before, a lot of chemistry is determined by those positive-negative interactions. And so when you have those water interactions with the ions, then that creates a really good, strong, stable situation, okay? It's interesting, too, to kind of look in detail about how, at a molecular scale, how the ions get surrounded by the water. In this instance, the negative ion gets all of those hydrogens surround the negative ion, and here all the oxygens surround the positive ion. So that's what it would look like at a molecular scale. Okay. Although this is true that those positive-negative interactions with the water are usually really favorable, that does not mean that every single salt is a term that chemists use to describe ionic compounds. They kind of use it as a generic term. So not every salt is going to dissolve in water. Those solute-solvent interactions are not always as strong as they are in, say, sodium chloride. In this instance, silver nitrate, they are, and so it dissolves, and we would see this as a uniform solution. It might not necessarily be clear, but it'll be transparent. So you can see through it, but it might be like a clear blue or a clear purple or something like that. In the case of silver chloride, which does not dissolve in water, those solute-solvent interactions are not strong enough to allow it to dissolve. It'll just sit at the bottom of the container. So you can really easily observe whether or not something is soluble just by whether it looks uniform and dissolves into the water or if it just sits on the bottom. And we have to have experiments in order to determine whether or not something's going to dissolve. So that's not something you guys can predict. So, you know, this is something that we actually come up with a set of rules that we tell you so that you can know from the rules if something is soluble. So again, don't forget as we're doing this, soluble means it will dissolve, and insoluble means it won't dissolve. So I give you these solubility rules on your exam equation sheet, but you need to know how to use them. So most of the things are telling you what will dissolve. Okay, there's lots and lots of things that won't dissolve. That's why after these first few rules, it says most other compounds are insoluble. Okay, so if it's not specifically highlighted on this list, you can assume that it is insoluble or will not dissolve. Okay, so the first set, all of the 1A elements, so this is in the first column, and NH4, those will all dissolve. It does not matter what they're paired with. So this could be like lithium sulfide or ammonium. I'm thinking of something else, not chloride, because that one's different. Ammonium phosphide. Okay. These will be soluble. We don't care what the negative side of the ionic compound is because these ones are all the positives. So there's going to be a negative pair with it, but it doesn't matter. All of them will be soluble. Okay. In the next rule, nitrate, NO3 minus, and acetate are always soluble. So on the reverse, it doesn't matter what the positive side is. If it's one of those as the negative, it will always dissolve. So like first, check the positive side. Is it one of these guys? If it is, you're done. It's soluble. You don't even have to go on. Next, check the negative side. Is it one of these guys? If it is, great. It's soluble. You're all done. So calcium nitrate, for example, would be soluble. The way we designate if something is soluble is we write AQ, meaning aqueous, meaning it has dissolved. So maybe I'll put that up here. This is the symbol. The state, if it's insoluble, you just leave it as solid. Okay, chlorine, bromine, and iodine. So we're still on the negative side. Most of those are soluble. So for example, calcium chloride would be soluble. Or even like iron chloride would be soluble. But there are a couple exceptions. Unlike the nitrate and acetate, the chlorine, bromine, and iodine have a couple exceptions. So here are the positives that when paired with them will not be soluble. So what that means is silver chloride will not dissolve. Mercury chloride will not dissolve. Lead chloride will not dissolve. Okay? But any other thing with chlorine, bromine, and iodine, calcium, iron, cobalt, gold, any of those would dissolve. Okay, last one. Still a negative, sulfates. Most sulfates do dissolve. Most of them will be soluble. The exceptions here, strontium, barium, calcium as well. Those are all the group 2 elements, so 2A, second column. So you're not going to have calcium sulfate dissolving. So that one would be solid. Whereas iron sulfate, because it's a sulfate and it's not an exception, that would dissolve. That's aqueous. Okay, and then as well, lead and silver, those would be insoluble or solids. They will not dissolve. Okay, so we're going to practice using these rules to define if each of these is soluble. So put aqueous if it's soluble, or insoluble, and then you would put solid. So pause the video now, use the rules, and try to determine these, and then you can come back and check your answers. Okay. Okay, so here are your answers. There's a couple things I kind of forgot to mention at the end of the rules, so we'll go back to those. So the first one was, I sort of said this, but if it's not specifically covered on the table, then it is not soluble. It is insoluble. So like we didn't say anything about, I think aluminum sulfate. That's one that wasn't covered at all. Yeah. So that there's nothing in the rules about aluminum compounds or sulfur compounds. So you know that it's not soluble. That's what this last rule means. Most other compounds are insoluble. There's a couple exceptions there. So sulfur, when it's with one of the column 2, is soluble. And hydroxide, when it's with the column 2, is slightly soluble. So it just dissolves a little bit. So those ones are kind of exceptions. So I guess, no, that covers all of those. Okay, so there's the answers again if you need those. Okay, so that's ionic compounds in water. And the next thing, I think I said, oh, no. Okay, the next thing is covalent compounds. And now we're going to talk about this both in water as well as in non-polar solutions. So remember, we say that water is polar, meaning it has a partial negative, partial positive side. So sugar, it happens, is also polar, meaning it has these, I'm just going to put like positive, negative to remind you that polar means it has positive and negative charges. Okay. We haven't really talked about that, so I'm going to cross that out. So when covalent molecules dissolve, they do not break up into individual ions. They stay as an entire sugar molecule, and the water surrounds that sugar molecule. Okay? It does not break up into individual carbons or oxygens or hydrogens because it's not an ionic compound. It doesn't have those charged particles. The whole thing has partial charges, and maybe just to emphasize that, it has those partial charges, and that's why it's able to interact with the water, but it doesn't break apart. The water just surrounds it. There are covalent molecules that are nonpolar. Okay, so an example of this would be like methane, or a common one we're going to talk about on the next page is carbon tetrachloride. Now, since you guys don't know yet how to determine if a molecule is polar or not, I would have to tell you that. One hint, if it's carbon and hydrogen, doesn't matter how many carbons and hydrogens, but it's only carbon and hydrogen, it will be nonpolar. Okay, so when we look at molecules, before we get onto that page, when we look at molecules, covalent molecules, and whether or not they will dissolve in water, we use this phrase called like dissolves like. Now, I should have had a whole slide about this. I don't know where it went. But the gist of it is what we've just been talking about. Water is polar, and if the compound, the solute that you're trying to dissolve into it is also polar, then they will mix and the solute will dissolve. If the compound you're trying to dissolve in is nonpolar, then we would consider that to be insoluble, or they would not mix. So like dissolves like, meaning similar polarities will dissolve in each other. Similarly, we can have solvents that are nonpolar. So carbon tetrachloride is a nonpolar molecule used as a solvent. So using this idea of like dissolves like, let's look at what we can expect would dissolve into carbon tetrachloride. So carbon tetrachloride is kind of the opposite of water as far as what it will dissolve, how it will work together. Okay, so ionic compounds, they're never going to dissolve in nonpolar molecules. They might dissolve in water. You would have to use the solubility rules to determine that. Water and carbon tetrachloride would not mix, okay, because one is polar and one is nonpolar. This one says that it's nonpolar, and so that one will mix. Oh, circle your answers. Which of the following would you expect to have a reasonably high solubility? Okay, so circle my answers. Cooking oil, nonpolar, yes, that would dissolve. Ionic, nope. Those only dissolve in water and only sometimes. So we'll label this column as in carbon tetrachloride. Then for part B, we'll say, what about in water? Okay, let's do the easy ones first. If it's nonpolar, no, it's not going to dissolve in water because water is polar. Water in itself, sure. That one's kind of funny. And then ionic compounds. So now we need to use the solubility rule. Okay, so sodium chloride will dissolve because rule 1 says all sodiums will dissolve. Check. Sulfate, usually down here, calcium sulfate. There's no rule about calcium, but sulfates are one of the rules, but we need to make sure it's not one of the exceptions, okay? So it says sulfates are soluble except when with these guys, including calcium. So this one will not mix into water because the solubility rules tell us that it won't. All right, last thing is acids. So acids are interesting in how they dissolve in water. So just to be clear, these are the only 2 slides where we're talking about things dissolving in stuff that's other than water. And that's where we're using this idea of like dissolves like. All right, so acids are interesting because they're kind of this middle ground between ionic compounds that break down into their ions and covalent compounds that stick together, like a sugar, okay? So there are 6 acids, this is the list, these are on your exam equation sheet, that dissolve completely, meaning that they break up into H plus ions. This is kind of the definition of an acid, is that it gives up an H plus from that molecule. And these 6 break up completely just like an ionic compound would. Okay, so if this was sodium chloride, you would see sodium ions and chlorine ions. So these 6 will behave just like a soluble ionic compound. The other acids, which is any acid that is not one of these 6, will dissolve, but it might only dissolve slightly. So this is what I mean about being a middle ground, is that it'll form some of these and some of these, but some of it will actually stay as that molecule. They'll dissolve, it's just how do they break up? So you can see this in this picture. They're all dissolved. There's no like solid sitting on the bottom, but some of them have broken into H pluses and the acetate ion, and some of them has just stayed as the acetic acid molecule. Okay, the way we represent that that's happening is with this double arrow to show that all of those species are present in the water. So again, they do dissolve. It's just how do they dissolve? Do they break up into ions or do they stay as an individual molecule? In the strong acids, they break up into ions. In the weak acids, some of them break up and some of them don't. Okay? All right, so we will go ahead and start here. I would really recommend, if you haven't already, to go ahead and do the homework that corresponds to molarity, because that is really going to be a matter of practice. Like if you did good on chapter 4, you're feeling confident, you're probably going to be fine. Just kind of whip it out and make sure you feel comfortable. If you struggled with chapter 4 a bit, then it's probably going to take you a little bit more time, and you want to spend that time now so that you're not rushing around, closer to the exam, so that you've got some time to ask questions. It's kind of surprising the number of people I don't hear asking questions until after the exam. And they're like, I did really poorly and I have no idea. I'm like, okay, well, you should have probably thought about that a little earlier on. So now is the earlier on. So looking at molarity questions and seeing what you're struggling with, then asking some of those, concerns. And don't just say, I don't get it. Watch some videos, read the textbook, try some problems, look at some of the worked examples that are in the textbook and see what you don't understand, okay? If you're like completely blank, I have no idea, that might be time for a tutor, because I'm not going to be able to sit down with you for 2 hours, every week and go through that. But like specific questions are really easy for me to get you a quick answer. I can make a video. You can email me. I can respond, with text. I can make a video for you. I'm almost always in John Jay Atrium from noon to 1. You can come by and see me then. You can come early to class if you're in the 10 o'clock class. You could stay after a little bit if you're in the 2 o'clock class. So I'm happy to answer those questions, but I really need you guys to take the initiative to be asking earlier on, because coming to me, a day or two before the exam and saying, I don't understand anything, it's too late, or coming to me after the exam and saying, I have no idea what's going on. Obviously that's too late as well. Okay. All right. Have a good day. Like I said, you can come to the Google Meet at the beginning of class if you had questions about your exam, and we can go over those then. Okay?